Hello, during this session I'm going to be talking about satellite orbital energy. The idea is to identify the potential kinetic and total energies of an orbiting satellite. Let's see how we'll go about doing that. If you think about the energy of orbiting satellites, we're going to start off thinking about the potential energy. This is something we know how to work out. If we have a satellite of mass m orbiting Earth at a distance of r from its center, it has gravitational potential energy. V is minus g mass of the Earth times r, which means its gravitational potential energy, or gravitational potential energy, is the gravitational potential multiplied by the mass of the satellite. So therefore the gravitational potential is minus g multiplied by the mass of the Earth multiplied by the mass of the satellite divided by r, which is the distance from the center of the Earth. Now remember that is the distance from the center of the Earth, not the orbiting height from the Earth's surface. It's one thing that people often make mistakes for. So if we graph these against radius, we see that potential energy looks a little bit like this. We see that the 1 over minus 1 over r shows that the potential energy becomes closer and closer to zero the further out it goes, and with the negative symbol it means that if we plot the potential energy against 1 over r, we get a negative gradient. So there's some things to think about, and you just got to recognize that you might be required to graph these. Let's think about the energy of the orbiting satellite, kinetic energy now. So what we know is by the law of universal gravitation and from Newton's second law, we can work out that the force of attraction is going to be equal to mv squared over r. Okay, so this is what we're recognizing, that the centripetal force is going to be equal to the gravitational attraction. Therefore, kinetic energy is half mv squared, and we can rearrange this to show that half mv squared is equal to gravitational constant multiplied by the mass of the Earth multiplied by the mass of the satellite divided by 2r. Okay, so all we've done is rearranged from the earlier statement. If we graph this, then what we'll see is the kinetic energy. Again, there's a 1 over r relationship, so therefore k is the constant of proportionality, and that equals to g mass of the Earth times mass of the satellite divided by 2. And there we can see the plotting of both the kinetic energy against radius and kinetic energy against 1 over radius, which is more useful because the gradient of the 1 over r should give me the constant of proportionality. If I think about the total energy of orbiting satellite, it's going to be the potential energy plus the kinetic energy. So here I'm going to show that I'm just going to add up those two values. So the total energy actually is minus g mass of the Earth multiplied by the mass of the satellite divided by 2r. The total energy is a constant for a circular orbit. Now, we're saying this is for a circular orbit. If you think about the planets, satellites of the Sun, they don't quite have a perfect circular orbit. But for simplification purposes, we're going to consider just as a circular orbit and say that the total energy is always constant. So graphs of energy against radius here, the total energy plots, we'll see that we still have a 1 over r relationship. We can see at infinity the total potential energy should be 0, edges towards that, and again that allows us to graphically show what we've spoken about before. So there's how we calculate potential energy, kinetic energy, and the total energies, and also to show how these things are displayed graphically as well. I hope this helps in the future.